This is my next project. I'm calling it ourBotManager, and it's a robotics project, and I'm just getting into robotics. I don't know a lot about it, so I'm actually going to do this in 3 phases because it's going to take quite a while. So the first one I'm just calling preparation. So that's when I'm learning more about robotics. I'm going to learn the robot operating system, ROS, and learn about actuators and servos and encoders and motors and things. So I kind of know the basics and how things fit together. After preparation, then I'm going to actually build my robot. I'm thinking it's going to be a Roomba type of robot where it can navigate around the house, can take pictures, get sensor data, can be remote controlled and can recharge itself. And then the last stage will be to actually build ourBotManager, which will be a Firebase backend, Angular front end. It's going to kind of inventory all my robots that I put together, keep an eye on them, manage them from a distance so I can find them, check on their status and things. So hopefully this will be an interesting project. I've created this checklist. It's one of 3, so this is for preparation during our ourBotManager project. So these are all the sort of learning and things I'm going to experiment with before I get into actually building a robot and then finally building the application to manage the robots I've got out there. So it could be a long project. So in this ourBotManager preparation, I've got the following tasks. So first one's to learn ROS version 1. Just started on that. What I'm learning on that is I may want to actually use the robot operating system version 2, so I've got down here to learn ROS version 2 as well, so I think I need both those things. I've got the courses arranged for that. It shows the link to courses on Udemy that I'm using for that. About halfway through this version 1 course, and it seems a good course. Other things I need to do during preparation is get some hands-on experience with just basic understanding of motors and encoders, things like that, to do with robotics. After that, I want to get some hands-on again, motors, movement, control, but using a microcontroller. So getting a microcontroller interface to that hardware, find out how to do it, and also I'll be using Micropython, so just seeing what I can and can't do with Micropython, because there may be some timing issues using Micropython rather than something like C, but we'll find out that in that tasks. I'm planning on using microcontroller to act as a node to ROS. I'm not sure how that's going to work yet. I think it may work better in ROS 2 than ROS 1, which is kind of one of the driving things for using ROS 2. So I'm going to find out that in this 5th task here, microcontroller to ROS interface. I'm also going to run ROS. I'm planning on running it on a Raspberry Pi 4, but I think I'm going to need to install an SSD, have it boot off an SSD to get the performance I need and the space I need to run something like ROS, especially because it's going to be using it Ubuntu as the operating system. So task 6, to work out all those sort of mechanics and making sure I can get one running. And then task 7 is just kind of a wrap up, catch all tasks to test connecting the Raspberry Pi ROS master to the node that I create with the microcontroller, make sure everything can work the way I'd expect, that I can actually get them communicating, that it looks like a node to ROS, those sort of things. And then that should be most of my preparation work. After that, I'll have another checklist for actually building the robot, and then finally a 3rd checklist where I'm creating the ourBotManager application, which is going to manage all these bots that I may make. Okay, here's the first test with my test bench. So basically I've set this up so I've got 12 volts coming from the power supply on these connectors here, and I'm actually sending the 12 volts both to the motor, so no pulse width modulation going on at the moment, just sending the full 12 volts to the motor. So the motor will be running at its top speed, and I also send it to the power converter here, so 12 volts in, 5 volts out. This 5 volts is going to my breadboard, and and is going over to the micro controller here. I'm not actually using the microcontroller itself yet, but I am using the 3.3 volts that the microcontroller has as one of the outputs, so really just using it as a power supply at the moment. And I've got that 3.3 volts going to this line here, and that drives the Hall effects sensor. So one side of the 3.3 volts goes to the Hall effect sensor here, the other side the minus, so the negative ground, goes to the other side of the Hall effects sensor, and then the output from the Hall effects sensor is going down this yellow wire back to the microcontroller. Again, I'm not using that yet. There'll be some of the tests I do with the microcontroller, but the other Hall effects sensor, because it has two on it, bringing to my oscilloscope so I can look at the waveform and how the size of the waveform that's coming out of the encoder. So let's turn on the 12 volts. So the motor's started up. This is a motor that should be generating 200 revs per minute with the gearing. And then that's been sent up to the oscilloscope, so I can see it on my oscilloscope. And when I look at the oscilloscope, it's saying it's generating square waves and at a frequency of around 750 hertz. So it's telling me for every second of rotation of this motor geared down, it's generating 750 pulses from the Hall effect sensor. So basically that's what my microcontroller is going to have to deal with, is 750 interrupts per second at the top speed of the motor. So starting on my microcontroller tests, I'm using the Raspberry Pi Pico. I've got it connected up to a OLED display just to be able to display things, and also have it connected up to the rotary encoder on the motor. So for this one I'm writing some Micropython. I'm using Thorny as the IDE at the moment. I'll swap back to Visual Studio Code eventually. So first I need to import from machine the pin, I2C interface and the timer class. From the SSD 1306, which is the OLED display, I bring in an OLED library for that, and then frame buffer to be able to print things out on that display. First thing I do is set up the motor encoder interface. So remember, I've got a pin coming in from the Hall effects reader on the motor. So first I set up a motor encoder count, so count the number of pulses coming in. I designate pin 10, GPIO pin 10 as a pin in. I set up a motor encoder callback, so this is going to be called on every interrupt, and basically all it's doing is adding 1 to the count for the motor encoder count every time it gets interrupted from the encoder, and then set up the actual motor encoder, which is that pin, as an interrupt, or responds to interrupts on a falling signal from the pulse coming in. Every time there's a falling signal, then it's going to call the motor encoder callback routine here and add 1 to the count. As we saw in the oscilloscope, it's basically a square wave, so this will happen every cycle of the encoder. Next I set up the OLED display, so I just define what's the width and the height of the display I'm using. I set up the I2C interface. I'm using the first interface on the Raspberry Pi Pico board, which is 0, and that's predefined. When you use I2C 0 interface, it's using GPIO pin 9 and 8 for that. So that's what I've got the OLED SD1306 connected up to. So I just set up a class called OLED for that OLED display. Then the final thing I'm doing is doing a status timer. So as I'm getting readings back from the encoder every second, which I'm going to be using this timer for, I'm going to do two things. I'm going to display what the number of motor encoder counts I've got, and then reset that count. So every second I'm getting I'm displaying on the OLED the number of pulses I receive from the encoder. And then finally I run that status timer. So I emit it, so it runs at a frequency of 1, which is 1 per hertz or 1 per second. And then it does the callback on this update status to do all these things of showing the number of pulses and then resetting the motor encoder. So let's run that and see what happens. So back to my test bench. You can see the OLED displaying 0 pulses at the moment. I turn on the motor, you see it revving up. I'm getting 744 pulses per second, and then I turn off the motor and you see it roll down to 0. So I was interested in just seeing how well the Pico and Micropython can keep up with interrupts. As we saw from the motor, it happily kept in sync with seeing 750 per second. So in this case I'm actually using a function generator to generate the equivalent of the interrupts, and I've got it set for 500 Hertz at the moment, and you see the Pico's reading that out as 493 pulses per second. Now there's a little discrepancy there. I'm not too worried about it. Let's push it up a bit. 600 we're staying in sync, 700 we're staying in sync, or sorry 800 we're staying in sync. Again, the discrepancies probably due to the timing interrupt. So every second it interrupts, displays the pulse value, and then gets back to collecting the pulses from the function generator. But it starts late each second because of that, so that's why we get a lower value for pulses. Okay, so we push it up to 1000 Hertz and 1500 Hertz, which is kind of equivalent to if I had 2 motors with encoders generating interrupts at the same time. So it's keeping up with that okay. Now rev it up a bit more. I'll go up to 2000 Hertz on the function generator. It's reading 1952, which is in the ballpark. Go up to 10,000 and reading 9700 pulses per second. Again, the sample timing is cutting into the numbers. Go up to 15,000 Hertz. So this would be 10 times what it needs to cope with 2 motors, and it's still keeping track of the interrupts for those. So I'm happy with that. And let's just keep pushing it up and see if it breaks. So going to 16,000 Hertz, 17,000 Hertz, still hanging in there. 18,000 Hertz. And something broke there, so that tells me don't want to do more than 18,000 interrupts per second. If I roll it back down to 15,000, it's tracking the pulses again accurately. So I'm pretty happy with that. I think for my needs of tracking 2 motors, Pico should be able to keep up with the interrupts using Micropython.